The institution and the presenters have done the best to make sure they've secured copyrights for everything that they're going to show. But if you do consider that you or somebody you believe is the owner, then please do contact the institution so we can either have it acknowledged or we can have it removed before the recording goes out. I'm going to just try and stop sharing my screen. So tonight we've got two presentations, each roughly of 25 minutes. The first is on the development of modular bridge substructures. The second is on the design of reinforced concrete structures for the temporary construction case. So the format we're going to use tonight is that we will hear from both presentations. We'll then take questions on both the presentations together. We'll have up to about 15 minutes for questions, and we will finish no later than 7:15. So our first speakers are John Armitage, who's a technical director at Ramboll, and Philip Robinson, who is a civil engineering leader at Laing O'Rourke. John's got over 20 years of experience in major highway and bridge schemes, including Queensferry Crossing, landside structures, motorway widening, and junction upgrades. And Philip is part of the civil engineering leadership team at Laing O'Rourke, and he focuses on innovation in the infrastructure sector and beyond. So with that, they're going to be presenting on modular bridge substructures into the digital future, and Philip's going to be speaking first. So if I can hand over to you.
Thank you very much. Hopefully that's coming through and everyone can see that. As Chris said, so I'm Phil Robinson. I've been working in the research and development group for Laing O'Rourke for the past 8 or so years now, looking at offsite solutions in infrastructure. John, do you want to just say hello quickly before we start?
Yep. Hi, I'm John Armitage, based in Southampton, Ramboll.
Okay. So I'd just like to take you sort of through a bit of scene setting. So I sort of joined the business at a similar time to the start of the journey in our sort of roads and offsite bridge structural development around eight or 9 years ago. And since then, we've been sort of working on two parallel work streams. One of them has been in the development of offsite modular solutions for bridges, and the other one has been around digital configuration of components. So not going back to the drawing board every time we start a new project, but utilising what we've done before. So I'll, as part of that journey, some of the projects across the top, I'll take you through some case studies of those. And we've worked with 3 different clients, Highways England, Network Rail and HS2, who all have, through the government targets and leadership, are sharing visions around digital and off-site. So hopefully you'll see these two things coming together in the lecture today. So I'll take you through the case studies around the products, and John will then take you through the evolution of our digital toolset, digital configuration tools. So firstly, start with A453. We raised the question of how do we build these bridges using an offsite approach? How do we design the bridges so that they can be manufactured and assembled efficiently and safely? We knew that precast bridge beams and steel girders were already in the marketplace at that time, and so we really focused our attention on which other parts of the bridge structure could be manufactured off-site. We worked with Tony G and partners at the time to develop the solutions for the precast piers and crossheads that you can see on the screen. But we also looked at solutions for off-site manufactured abutments. And we developed a system which I'll just hopefully be able to play a quick video to show you that. So we developed a system for this where we were utilising precast shells for the outer faces of the abutment. We would place those on top of the completed pile cap where the projecting reinforcement was coming through from the starter bars. We'd then place the reinforcement, fix the reinforcement in the centre of the wall before placing the end closures and the front face panels, so that we were actually pouring a in situ core down the centre of that wall. And each of those panels then had a joint that was sealed with a wet grout solution. So that was the overall sort of construction sequence. That gives you a flavour of what we did on the project, and we were finding that on that we were generating around a 25% labour and programme reduction per bridge, with a 6-month overall programme saving. So we were we were in a place of thinking this is going in the right direction. So we then moved on to our next project, taking the lessons learned with us from the A453, and we continued to develop our abutment solutions for that project. This was working with the Staffordshire Alliance, which included Atkins as the designer and Network Rail, and Volker Rail for the main rail systems. We looked at how you take the methodology that we developed with the precast shells and panels on the first project and turn that into something we could actually utilize in pre-assembly areas. So rather than bringing the actual precast panels to the work front, we brought our precast panels, the reinforcement, to a pre-assembly area. We pre-assembled them into a 3D module, into a lifting frame, and then we lowered that into site. Sorry, that video just clicked away. But you can see the precast shells being lowered into position. And so that was working for not only the bridges that cross the mainline railway, but also some of the smaller bridges that were involved in river diversions. And so you'll see the images down the center of the screen in the bottom right of one of the smaller bridges. It used exactly the same methodology, but we delivered that bridge in a week. So from completion of piles to concreting the deck, that was a week's worth of construction. So we knew things were working at both scales, and we were onto something that was a system effectively. Interestingly, on this project, there were 6 bridges that we constructed using Offsite methodology, but there were 5 bridges that at the time when we looked at the rationale for delivering them, we decided to use a traditional approach. As it was perceived, they weren't on a critical path, and the program benefit savings that were on offer for them wasn't worth going down that route. However, things change on projects. Things don't go to plan. Things move around. So suddenly those bridges did come on the critical path, and the feedback from our workforce was, why aren't we doing these in the same way as we did before? And I think it sort of was the first moment of us thinking that there's a benefit to the wider application of this across a scheme as a system, and the benefits you get in reduced labour and workforce across a scheme deploying the same system. So that's the sort of lessons learned we took away from that particular project. So we then moved on to East West Rail, which was East West Rail Alliance, which was again Network Rail with Atkins, and we took the lessons learned again, and the lifting frame that we showed on the previous video and slide. It's not simple to hold all those precast panels in without them twisting and suffering from how the tolerances might suffer because of that. So we thought to ourselves, why not cast the concrete box in the first place and transport that to site? So we developed a modular shell system which allows the abutment shells to be stacked to the full height of the abutment or wing wall, or pier, as we've now been looking at as well. Rebar cages then lowered into the voids within the centre, and then the concrete is poured to the full height, and they're designed to resist the full hydrostatic pressure of the wet concrete. This solution was developed across 2 projects, both with East West Rail and HS2. So we had Atkins, WSP and Bramble all working together to come up with a solution across 2 projects. This had to go through approvals for Network Rail and HS2, and as Highways were adopting some of the HS2 bridges, they were also involved. So there was a lot of collaboration to get this to delivery on both projects, and you may have seen some of the East West Rail footage recently released on YouTube that's worth taking a look at if you haven't seen the Bletchley flyover reconstruction as part of that process using the same system. So then I'm just going to go through a few slides of how that was then deployed on HS2 before I hand over to John. So manufacturing, offsite doesn't necessarily mean things are efficient to manufacture. One of the benefits of the modular system that we've created is there's enough repetition in this across the bridges on a scheme, and then the opportunity to deploy it across multiple bridges across the wider industry, that it helps to justify the investment in the manufacturing process and the molds and things. Whereas if you're just doing one-off bespoke casting, you've got a sort of a different business case to deal with. So John will talk more about sort of how we've walked through that journey of developing products that we can then, but with sort of maximising the different number of configurations, but with a minimum number of products, and sort of to generate that efficiency in standardisation and manufacturing. But you've got to understand the rules around what drives the product to be a certain shape or form or size that it is. So is it that you might be able to transport something that's very large, but is that the most efficient for craning and lifting on site, or how big should the product be? So in this case, in the top right, you can see the picture of the trailer with 2 of the modules on the back. So deciding whether you've got 2 modules or some singles, or what's the height of the module. So all those things help to drive the geometry of what you're trying to design. Then moving on to site, there's a lot of learning that we've done in this space around what level of control do you need to put in place in order to control the tolerances of the on-site activities, which normally have a lot of play in them because they recognize that in a wet environment and a cold environment can be often difficult to achieve, versus the really tightly controlled tolerances of our offsite manufactured precast components. So as part of this process, we've developed jigs and frames that allow us to control the tolerance better than would normally be achievable, and that extra time in the on site, although it's seen as a bit of extra time that you wouldn't normally spend, actually really allows us to accelerate once we get out of the ground and into the assembly of the shells, and avoids clashes that would otherwise occur. Here you can see some of the shells going into place. There's a gasket on the bottom, similar to tunnel gaskets, that is designed to compress under the weight of the shell, such that when we pour the concrete to the full height of the abutments, that we don't get grout leakage, and also that means we don't have follow-on activities for sealing joints with wet grout or afterwards. So that really releases the rapid construction assembly. Then we move on to installing the prefabricated column cages that sit within the shells. Again, using jigs and frames to make sure that we control the tolerance such that they slide inside the precast unit that's manufactured to offer repeatable mold, that we know what the geometry is, but also that we avoid clashes with the starter bars that have been set out in the bottom of the bottom that you can see down there inside the shells from the pile cap. So all the time thinking about how do we control the tolerances between our on-site and off-site activities. Once the abutments and wing walls are complete, we've then got a connection of our L walls on top that help to form the wing walls, and they've been developed with a range of slopes on those to suit the different earthwork profiles that might be required. And then moving just finally on to the elements of the construction that are still in situ, and trying to standardize and simplify the most complex activities that are on site. So the diaphragms themselves are normally an area that has a lot of complexity and a lot of dense reinforcement, and a lot of carpentry and formwork involved. So the benefit of the shells has been the depth of the shell that we've actually got allows us enough space to sensibly construct the diaphragm. We've got precast fascia infills that sit between the beams to form the front face closure panel of the diaphragm for when we're pouring the concrete. You can just see on the left hand side the end closure on that there. And again, that takes a little bit more effort in placement of the beams to make sure when you're offering up the precast elements between the beams afterwards that's going to fit nice and snugly in there, and there's not a great big joint to seal. But it can be done, and that's the sort of the thinking and the efforts required first. And then to sort of bring that to life, just got a video clip of the actual abutment all coming together. So you'll see here, it's more of an assembly site. It's not a construction site in its traditional sense. You can see the starter bars projecting from the pile caps, and we can see the precast elements being lowered into place in here. There's a team on this of 6 that assembled this abutment. This was 400 square meters of abutment in 5 days of construction. So that's including placing the shells, dropping the rebar cages in, and completing the concreting works, the in-situ concreting works. The team of 6 are a multi-skilled set of bridge assembly teams. So rather than having carpenters and steel fixers and different resource demands on what team is required where on each bridge, we're using multi-skilled teams that can do all of the jobs rather than just their individual trades. You can see the cages there ready to be installed and lowered into the cores themselves, and then we should eventually start to see the reinforcement being poured. But you can see it's a relatively tidy site compared to what would normally be construction. You can see we're able to still achieve the same sort of rates in productivity during the wet days on site as we were the dry days. So still, and because it's a simple, repeatable process, we're in a space where we can still do this safely, reducing the risk of accidents. So I'll close that. And then just to sort of give you a summary of the benefits on there, the abutment was assembled in 1 week rather than constructed in 7. So when you're working at prelims of maybe £200,000 a week or more on some of these schemes, there's a potential for substantial savings across the scheme. Overall, we're finding that we can sort of, compared to traditional, we're around 50% of the construction for an entire bridge. There's 6 people on site rather than for 1 week, rather than a team that we estimate of 12 for 7 weeks on a traditional abutment. We've got the benefits there of the fact that we've got less resources on site. We've got less site cabins and setup and facilities there for the team, which therefore can feed into our carbon calculation there in terms of what's the potential carbon saving when you're running off diesel generators with large office setups to support large teams. So that's part of that carbon calculation, along with the embodied carbon within the concrete itself. The ability to have the precast shells means we can have a higher cement replacement in the core in situ core concrete, because we're not trying to get the concrete to go off quickly so we can strike the shutters and remove all the temporary work. So that increase in GGBS and hopefully at some point moving towards a cement-free solution, working with the client bases on what departures we need to get that approved. And then the other benefits, obviously, in terms of reduction on site, we've got fewer people, less time and repeatable processes, so we're safer overall. And the improved quality control in the factory environment with a simpler construction sequence on site is leading us to fewer defects, which from a client perspective should lead to reduced maintenance in the longer term. So hopefully that gives you a feel for what we've developed in the product sense. And I'll now hand over to John to talk through the digital tools that we've developed as a team to help drive this approach across many projects in the future to come.
Good. Yeah. So one of the challenges of this type of form of construction at an early stage is there's clearly quite a lot going on in terms of component selection. It's how do we assist engineers at the early feasibility stage of a project to understand whether it's feasible to go down this component product-led approach. So it's about 2 years ago we started a project funded through Highways England Innovate UK, obviously with Lang & Rourke and BBA for assurance, and from the design front, Ramble and WSP working in parallel. Us having been the designers on the HS2 bridges. And what we're looking for here is to have this product-led approach, looking for pre-approved components so that there's confidence in the system, very much around engineering-driven decisions, looking for as much automation of the process as possible, generation design outputs quickly, having design informed by cost and not just costing the design that we've got. So what we had to do was to pick we wanted to limit this down to a structural form that we knew we could do. So it's, again, leading on from HS2, we had a single span integral bridge with full height abutments, pre-stressed precast concrete beams, and the precast shells. And through that, we're taking the process of HAPAS certification to get the assurance, which is where BBA are involved. We've got an improved installer scheme, a design guide, and an installation manual. And the aim of this is, at the end of this process, you've got design validation. You've got a design that an engineer can be confident can get taken to the next stage and be developed further at detailed design. We want to have a 3D model that can be used in preparing the deliverables for the scheme, an AIP and drawings, and also all the data needed for cost validation. So where do we start on this? Well, obviously, early on, you've got some key decisions you need to take about constraining the extent of this task. And one of the big things about that is getting all the experience in the room together. What was really important was to have the contractor, the designer, the precasters, and the installers all working together. And from this, we had various discussions over how to, what were the range of parameters that we'd need to look at to get this to work. very much aiming for realistic bridge configurations, one that are reflected out in the bridge stock in the UK that's going to be built in the next couple of years. Also conscious that we need to maximise the data set that we were going to achieve, but also make it achievable given run times for analysis. And a big part of this was actually defining components and getting a common understanding of, are we all talking the same language on span, abutment heights, that sort of thing. So what we ended up doing was taking, we want to make engineering-based decisions, and we're looking at this from a global perspective, but also from a local perspective. So on the global perspective, we want engineers to have the confidence that if they generate a bridge configuration through this tool, that it's something that's capable of being developed at the next stage of design. And one of the problems about integral bridges is that there's a lot of soil structural interaction going on. They're not easy things to design. So what we did was we looked at a number of ranges in here. So we've got span up to 40 meters, skews up to 30 degrees, various abutment heights, and also a selection of categorization of ground condition into hard, medium, and soft. Very basic, but then at an early stage in the scheme, you might have only got some very basic information on ground conditions because the GI is not taking place at that time. We're then running multiple analyses in Sophistic and LUSAS to generate the data, numerous data sets, so that an engineer can then see the data relevant to the bridge that they're selecting and understand how heavily the various components are being utilized. So this shows the output from the Sophistic model that we used. Obviously, WSP used a LUSAS one in parallel so that we're cross-checking against each other. And through here, we've got a single data file has been used to generate what is effectively a detailed design model. But with just changing one number in the inputs, you'll then change that from a 10 degrees to a 30 degrees skew. We're then selecting out the key sections which constrain the design at this point. Otherwise, the runtime was going up from sort of 15 minutes to 4 hours, and we couldn't live with that. But from this, we're generating the data that we need, but with also a degree of confidence that later on we have run the key load cases that are going to be considered. And one of the other things that we wanted to do through this was actually to calibrate what we were doing against the HS2 bridge that Phil showed earlier. We're then looking at assembling all the product components into the configurations, and again we're looking to maximize the number of products, or maximize the configurations, but with a minimum number of products. So you can see in green at the bottom, there's quite a useful component there that can be used to put a curve into the wing walls, which is quite nice, but was also very important for us on HS2 to get an angle of 15 degrees back for the train impact case. What comes out the back of that is a design guide, which is intended to be used by experienced bridge engineers, but to answer those questions that people would have using the system. And into this, we had a lot of decisions around the local rules. How much should beams be embedded into the abutments? How long should a stub wall be to enable you to pick up the ground lines and carry the loading from both parapet impacts and also the integral bridge pressures on a skewed structure? So a lot of rules were generated through that. And then finally, to input into the configuration tool, we need to, again, define clearly the data that we're looking. So we've got a data input sheet that actually enables someone to list out the parameters they want looked at for a particular bridge structure, heights, heights, abutment types, and that sort of thing. So finally, we end up with a configured model, as you can see on the left, which is a 3D model that can be exported out to IFC. That's developed, the Langer team have done that using a SolidWorks-based platform. And that exports out to a drawing at the top, which can be used as the basis for an AIP drawing or an options report. It does actually generate a template AIP as well with the key data and key analysis methodology already imported into that. And also there's a set of cost data. And finally, on to design program. We're anticipating some quite significant savings in design for this, not least through the use of more standard analysis models, but also just from the common process, common methods of detailing, common methods of doing things, and that should yield a good process. And so we just do a final comparison of traditional against product-led. One of the issues we've seen on the traditional process is you try and shoehorn modularization into the process at a later stage. It's quite difficult to do that. You're very often too far down the line to make the best use of the components. Whereas if you take the product-led approach at the start of design and then understand how you can then adapt that, we can have different spans, different SKUs, but we can use the components to generate different structures. We can then select how that works. And I think we've got a final slide there, which at the moment we're running, it's a 2-hour process from selection of the data through to output of the data on the right. And I think Phil's got a short video just to show, it's about 2 minutes, just to show the process, if that's okay.
Yeah, right. So just to finish on. So this is basically a speeded up run through of inputting information into the tool. So providing your information about who you are and what project it is, providing things around the geometry of the bridge in terms of skews and spans, looking at the obstacle and what you're trying to cross and the relationship with the bridge to it, and then getting an output to just check that you've input that information correctly and you've interpreted the drop downs correctly, so you're seeing what you're configuring. Then selecting beams, then getting feedback on how hard the structure's working. Like John said, those 2,000 bits of data in there can be filtered to then see which the closest fit to your bridge and see how hard it's working. Based on the selection of the beams that have been made in the sort of schematic stage of the design, we've got that you can see the model is starting to increase in detail. Then there's similar decisions around wing wall configuration. So we can see the sort of schematic placeholders there for the wing walls and the stub walls going in at the back of the diaphragm. Again, the level of detail building all the time. Then we're just checking to see that information's come through from the schematic stage of decisions before we start loading in the actual components into the model. So we can see, rather than just being the space savers, we're now starting to bring in the actual deck. We're bringing in the beams themselves and the diaphragm. It's a view here of showing the beams with the infill concrete at the ends, the permanent formwork in between the beams. And then similarly, again, making decisions about foundation layouts and the requirements for parapets and different heights of parapet or different containment requirements before we then get to a completed bridge automated from the decisions that we've made within the tool. So really quick run through. I appreciate that's a quick fly through, but you can see that the level of detail that's within the model is not just an IFC sort of volumetric model. It's right down to nuts and bolts level of detail. So with that, thank you very much for listening and happy to take questions at the end. Back to you, Chris. Thanks
very much, John and Philip. That's great. I mean, it's for me, it's certainly really good to see the integral connection being developed, because I think I was a little concerned to begin with that it was promoting use of bearings to keep it simple. So it's great that they've got that development. And you've also answered a question that I had about carbon as well. I wondered whether, because we're using more concrete, whether it wasn't so good from the carbon perspective. But you've identified all the areas of savings there. So I think that's really good. But no doubt there'll be plenty more questions coming later on. So I will invite our next speakers to share screen now then, please, perhaps as I introduce you. And they are David Kwong, who's a principal engineer at Wentworth House Partnership, and Ioannis Vafougis, who's an associate also at Wentworth House Partnership. David's got 10 years of experience in temporary works and geotechnical design, working both as a consultant and a contractor. And Ioannis is a specialist in temporary works and has an MSc in earthquake-resistant RC structure design. So they're going to be presenting on the design of reinforced concrete structures for the temporary construction phase. And David is going to be speaking first. So over to you, David.
Yep, thanks very much. So general presentation is just talking about sort of the sort of temporary works and that you sort of generally come across the an RC environment. And sort of general outline of the contents of the presentation is highlighting almost common temporary works that you sort of come across, sort of from cradle to grave, of what you generally see, and sort of just evidence of this, which Ioannis will talk about later on a couple of projects that we've recently completed on. So just general introduction, obviously from the sort of pictures that you can see here on my left and on the right, is especially working in congested city centres, obviously where space is limited. The general project cycle is taking a existing structure, doing demolition of that, and then building on that new developed area. So obviously that just gives you an example of what we generally kind of see more and more, and whether it be demolition or partially restrained structures, obviously we see that more common on everyday life. And I suppose more and more projects you do get a lot of basement excavations, which will obviously allow the superstructure to follow through. So almost just starting at the beginning of any project with regards to sort of demolition is, and one of the first sort of temporary works you sort of come across is floor load tests. So, whilst we obviously do ask for investigations to be carried out on site to sort of verify thicknesses of the slabs and the reinforcement intent, it's what you generally do find quite hard to prove is the bending and shear capacities of the slabs, and proving it to a capacity to a degree that allows you to put a substantial size excavator on top, which obviously helps with your program in terms of demolition. So one of the first things that we normally do is floor load tests, where you almost take a typical bay and you test it to certain loads of machines that you'll be using on, and just to sort of determine its behaviour. Obviously, what one of the quite significant sort of challenges and main things to be mindful of is flat slabs that you generally come across. So I'd always advise to do calculations just to sort of justify that and sort of generally prop those areas before any load testing. So once you load test the back and sort of dictates what kind of plant machinery that can go on, or if there's any back propping required, that then takes you to sort of the back propping, which allows the demolition of the existing structure. So sort of that picture on the right, you can see sort of little excavators in the background, just working on existing slabs to help bring down the existing building. But sort of similarly, just on the topic of back propping, it's very useful in the event of propping to help form the construction of new permanent slabs. It being used in formwork, force work, and obviously subsequently, depending on the site or the nature or where tower cranes or certain bits and pieces are located as part of that construction phase, is sometimes we do need to obviously end up back propping new permanent slabs, even just to allow whether it be a mobile crane to travel on the slab. Pin for beam. So with certain buildings now not being fully demolished, but almost a cut and carve, you do come across this typical pin for beam. Is how do we sort of go about forming large openings within existing structures, whether it be an RC wall, and then forming a pin for beam is just a useful application of temporary works, where we sort of typically knock out at meter spacings and puts will be UC stub sections as stalls. So you can see sort of the picture there. We can see sort of 5 stalls being placed in, and then that allows sort of all the intermediate sort of remaining bits of the wall to be demolished, and then allows you then to sort of feed your reinforcement through and concrete that up. So, and then that allows you to sort of knock out your opening from below. So generally, when the existing building is demolished, especially in and around London, there's quite a lot of buildings which either contain a single-story basement. So other temporary works elements that you sort of do come across are propping of the existing basement walls, whether that be, and sort of depending on what the new structure is or the scope of works, is either you generally prop down to sort of the down onto the B1 slab, or if there is sort of follow-on works for the piling contractor to come along to install a new secant or contic box, they're all found onto thrust blocks. So sort of just moving on throughout that project life cycle. It's not uncommon to sort of, you find a new basement within an existing basement. There's obviously several ways that these can be constructed, is whether you end up looking at sort of that bottom up basement construction, you know, where whether it be secant or contig piles sort of being installed, and effectively trying to get those being designed for that sort of temporary condition, you know, to allow you're almost propping, say, at the top of the cap and beam, so you're getting that permanent works cap and beam sort of acting in the temporary conditions to allow it to span between props. I suppose what's obviously quite useful as well is to form blisters and corbels above cap beams, and then that allows at least the permanent slab to be cast up against the cap beam, and then you allow your props to be removed after, so which aids the removal of the prop sequence. And like I said, like in terms of when you sort of design those contig and secant piles, you know, design them for that temporary phase, just to allow them to sort of almost excavate down to B2, or whether you have to introduce intermediate propping throughout. So the other sort of form basement construction that you see is the top down, and I suppose it's all dependent on price and program. Obviously, with the top down basement construction is how do we go about making the permanent work slab act in the temporary conditions. So sort of you see there on the picture on the left, it's almost a donut slab. So it's either whether assessing that for whether the permanent slab needs a bit extra reinforcement, but then sort of the subsequent sort of knock-on effect and benefits of that is, you know, whilst you are installing sort of temporary plunge columns to help support the new permanent slab, it's almost not uncommon to use these permanent slabs as gantries, really. So depending on sort of the basement excavation phase, and as you get down to see whether it's your new B2 or B3, obviously one quite good thing to, and obviously a lot of contractors like to do as early as possible, is erect that tower crane up, which obviously can help you know, move material in and around site. So it's looking at how much of that new basement slab needs to be constructed and what sort of additional reinforcement is required in that area of the new basement slab, just to allow your tower crane to be constructed, which is obviously very useful to get your project going. And then sort of once you're down and you start building out the ground, getting your superstructure out, is whether you look at sort of the general core stability, so whether it be in the form of slip form and jump forms, and generally assessing these in the temporary condition, because obviously whereby in the permanent condition these cores are all supported by all your slabs at all the different levels. It's how much, and depending on the height of the new building, it's how much of the core can be constructed, whether it be in advance of lobby slabs or in advance of permanent slabs sort of joining into the new core. And obviously what you generally kind of see is another tower crane sort of erected on top of the core, so it's checking that in the whole temporary condition. So what I'll do now is I'll pass you on to my colleague Ioannis, and he'll just take you through a couple of case studies of sort of these being in application.
Good afternoon, all. So we will move from the general view of temporary works to more specific cases. So one case is the Nova East project that we, as well with house partners, were the temporary works designers for the for Kelbrek, which was the contractor of the early stages. This is our team here. So the place is just south of the Buckingham Palace, near Victoria Palace Theatre. We can see that the specifics of this plot is that it was a very congested plot, and had a lot of underlying LUL and Thames Water assets. So they had the King's Collar Pond sewer, for example, passing. All of the permanent work was designed around the underlying assets, and of course this was the main constraint of building up the building. So just to have an idea of the underlying the underlying assets that we they were the constraints of the site. The building is an 18-story building overlying of 3 basement floors, and it was built around the underlying assets. So the main characteristic of the building was that a large part of it was supported on these capping beams, and there was a very big pile cap that was actually cantilevering to support essentially the complete building. So in plan, we had a partial deep basement. The the rest of the building had a more shallow basement, and that is the basement 1 level, which is almost in the middle of the excavation. So just an overview of the elements that in a typical project we would design, considering also the construction element, the permanent construction elements that have to be designed also have to be checked for the temporary case. Is of course the bearing piles, is the retaining wall piles. In that case, the pile cantilever slab, the capping beam, the first level retaining props, the capping beam, the second capping beam at the lower level, the second level retaining props. There was an excavation gantry. All of these are putting all the permanent works in different load cases. The construction of the temporary case of the pile cap with the tower crane on the top, bearing piles, another pile cap. Then, of course, is the 70-meter high core stability with a tower crane on the top of it, and then all the excavation and the enabling works to enable the construction of the shallow basement. Of course, all of this have to come along with an assessment of the KSPS sewer that is affected by the construction sequence of all these assets. And of course, various outrigger cases to facilitate the construction. So we will see 4 of those designs a little bit more detailed. So the pile cap 3, which was named up for the specific project, had 2 cases in plan. So the first part was going to be cast, and then the second one, the tower crane would be on the top. Then the second one. So in the first stage, the tower crane had to be fully functioning, and because of the nature of the pile cap, this was designed to be a 3-meter deep cantilever pile cap. So there are specific assets that are included in this case. For example, the sequence of the pour. You need to design temporary case for the 3 different pours. So in each of these stages, separate temporary works, separate temporary reinforcement have to be designed for the functionality of the pile cap. And then we put on top the tower crane that started to service the site. Of course, we designed all of this in all the stages that were involved, against of course cracking and shear and moment. And then another specific problem that arises in such structures is the stability of the cage, which is also a high risk element. So in this particular construction, we had to deliver detailed designs of the cage, as we had 12 layers of reinforcement, 12 layers of reinforcement on the top. So we went down to the detailed design of the tie detail option, and of course we designed the cage for stability, because that was going to build completely from the top, rising 3 meters high, and also had a lot of hazards and health and safety issues. The temporary condition for the reinforcement cage, the Temporary Works Forum has been issuing some guidance, which you might want to have a look in. The permanent works, of course, the basement excavation. You can see here on the left the complexity of the basement during the construction and the temporary case. A typical sequence that we had also in this case was that the installation of the piles, excavation, installation of the first strut, further excavation installation of the second strat against the second level capping beam, then down to the formation level, and then construction of the permanent works. So in this case, the initial design was to install the B1 before to install the B1 slab, basement 1 slab, and then remove below that the strat, which changed eventually. Of course, we consider all the interaction of the soil and the structure, and we had some alluvium at the high levels, which is quite an onerous condition, and all the deflections had to be limited to 0.2% according to the specifications. And of course, in most of these cases, we design for at least 20 kPa general cell to accommodate the plant working on the side of the excavation. Of course, we designed we checked the design in 2D and 3D to have as much as possible exact deflection assessments and total displacements. And then, as this is almost this always happens, construction sequences change, as I told you before. So now the contractor decided, because there was a health and safety issue of hot works under a confined area, to remove the props, to change the construction sequence, and requested from us to evaluate the condition of removing the strat just after the B2 slab. That changed, of course, a lot the sequence and the conditions and the loads that the permanent works were to be exerted in the temporary condition, and so we had to model the complete structure in order to evaluate if the two slabs for those cases can work as a strat, as a strat in plan, and transfer safely the loads while being maintained within the specification and the requirements. Of course, we did the analysis and the assessment of the in-plan compression stresses, and that is an overview of the site with the construction of the start of the construction of the core. Here is a picture of the site with the gantry, and the core has just started. Half of the core is going into the deep basement, and the rest of the core is founded on top of the big pile cap. The core assessment is the stability of the temporary stability of the core assessment is always the case in this kind of structures. In just to overview the problem that we have in these cases, for the specific core, it's a 75-meter core. It has to stay 6 months without the surrounding framework advancing, because then the second contractor will have to come and build up the steel framework. The core should be designed also to accommodate the full working tower crane on the top, and it will be constructed with a slipform formwork, and the slipform would have to advance 6 floors ahead of the construction of the lobby slabs, which is always the case. Of course, there are design assumptions and SLS and check requirements according to the Euro codes and the serviceability control checks. The loading, if we break down the loading in those cases, you usually have the dead load, you have the slip form, which is mutually exclusive with the tower crane loads, the construction loads imposed on the lobby slabs once these are constructed, the crane loads, the wind loads, and of course the equivalent horizontal loads. And these also are accepted to the core to different construction stages that they have to be evaluated. So we apply the loads for different cases, and we need also to assess the core in terms of buckling for the two intermediate stages, because the contractor prefers the lobby slabs, and it's almost that the case that the lobby slabs are following the advancing of the slip form, which is much faster. Full analysis on the core in order to evaluate and design the temporary reinforcement requirements for those cases. of course, evaluation of the serviceability results and the deflection, the concrete incorporation, and the crack limitation that was defined by the permanent works designer. This is an overview. This is an overview of the core. Just before we had the tower crane on the top, which is a special case. The tower crane on the top is something common for high-rise buildings. You can have assemblies with 8 or 4 supports on the core. For the design of this type of structure, someone can use the Series 761 guide, which is the tower crane foundation type design. It has examples for these cases in. Of course, the worst locations come from a 360 degrees problem. Apart from the design of the main steel members and the connections, what is of interest in our presentation is the connection design to the core, which in that case, a special requirement was made for the precast core cap to be in place before the installation of the temporary crane. That, of course, increased that upstand distance here, which makes things a little bit more onerous. In that case, we designed the tower crane, the anchor of the tower crane, to transfer the load through lapping on the existing reinforcement of the core at the top. Therefore, the reinforcement of the core at the top, the crown, if we can say it like that, has to be completely redesigned in order to be able to undertake those loads through the lapping. And of course, special cases, special considerations have to be made for bursting loads and allowable stresses in the concrete and anti-bursting reinforcement around the cores. The bank building Belfast is a case that it is an example that will show us that some constructions are dictated by totally different constraints than someone can have when he's designing a permanent structure. This was one of the oldest frame buildings in Ireland, early 1900s, masonry walls, iron steel frame, and it has undergone a significant fire on the end of August of 2018, which burned the building from top to the ground. The challenge here was that since the building was burned, it was a very big health and safety hazard for the public, and at the same time to make secure the building after the disaster, a significant part of the center of Belter had to be closed down. So that had a significant cost effects. So the challenge here was to make safely as fast as possible, to remove the unstable elements, to install pedestrian protection, to build up the facade retention because it was a listed building, and to reopen the roads as fast as possible. Of course, in order to design the facade retention and to have a design that is the most efficient, we did have a wind load model to define as exact as possible the wind loads, which would bring us eventually to the design of the towers that supported the facade retention. In that case, since the Belfast is a port city, there were a lot of containers around the loads and lashing equipment. So we decided to use to innovate a simple modular structure made out of containers and backfill them for the ballast. Now the requirement here was the problem here was the design of the foundation. So for the design of the foundation was on top of Belfast slits, which is not just a good underlying a good soil. So we had to come up with a solution that will require less working hours of personnel working close to the dangerous building, and at the same time we will not be able to install a typical foundation for facade retention, which normally is for coupling micropiles working in tension and compression against the wind loads. So we ended up designing pad foundations with pad foundation with lock nuts on the pads, and we ended up designing the foundation with fiber reinforced concrete without the reinforcement. So in that case, we choose to use a little bit more advanced material with a 35 kilogram per cubic meter of the fibers. And of course, we had also to consider the settlement of the pad foundations onto the ground, and do not allow large deformation on the surfaces. So that followed CBT tests around the facade and extensive analysis for settlement. That is an overview of the project with the towers and the foundations. And we were fortunate enough to have Thomas Telford Prize for paper on the forensic engineering. Whoever wants to have a look on the other aspects of the project apart from the foundation, and we had the award of the Temporary Works Initiative of the BCI Industrial Works. Thank you very much.
Well, thank you very much, David and Ioannis. I think some really great examples of, I think, really where the temporary works design is much more complicated than the permanent works design. That's great. So we've had quite a few questions in. Sorry, there seems to be a bit of an echo on the line. I don't know where that's come from. Let's start off with one for John and Philip. So Andy Truby asks, with your modular abutments, do you use self-compacting concrete for the core infills? And as a sort of a secondary question, do you find problems with grout leaks at the joints?
So answer the first question, no, it's not self-compacting concrete, it's a high flow mix, and we did coring and testing on the trial that we constructed for East West Rail to check that we didn't have any honeycombing or anything down the bottom of the tubes to make sure the methodology was right in compacting the concrete. So we didn't want to have to go through departures or anything like that for the bridges, so we've kept that to within code. And then the grout leaks, so on the trial, that was what we've tested in terms of performance of the gasket, and so we've changed the gasket after the trial, so it's a great benefit of doing it to get that to compress. So we've not had any grout leaks on site since we've developed moved on from the gasket, so it's worked well.
Excellent. Okay, thank you. We'll just stick with you for one more, and then we'll move on. There's quite a number of people have asked effectively the same question. So Vidya Thamandra, for example, Ahmed Al-Irani. They're all basically interested in what sort of connection, if any, is there between the in situ and the precast, and is it composite?
So if I take that one from the design perspective first, there's a big it's obviously a big debate that happens on here: is do you make them composite or not? And for the bridges that are covered on HS2 and on East West Rail and through the Innovate UK project, they're not composite. Effectively, the concrete is cast against the steel shutter, which as a bridge engineer grates a little bit because you worry about losing the capacity, but actually the additional complexity of having to provide that shear connection is enormous, and potentially removes for a huge amount of the benefit that you get from the rapid construction. That's for the abutment columns. There are other elements such as the stub walls where we do take account of the composite action. So it's very much when you develop the component set, making sure you're using the best of precast, best of in situ, and stitch them together. And that did come about off the back of feedback from previous projects. And Phil, I don't know if you just touch on the previous ones that have been done and how that fed into our decision on HS2.
Yeah, so if you think about the original A453 slide that presentation we showed, that had the projecting reinforcement coming out of the shells, and we did on that project and on some bridges mobilised part of the precast in the compression zone. The issue with that is that as soon as you have that projecting reinforcement coming out, you actually then you have to have an open face to lace reinforcement into it. So actually having two faces with nothing projecting from them and being able to drop a cage down the middle without any clashes in that space was a real benefit. And on the East West Rail project, the asset managers didn't want they wanted the shells there as a protective layer and didn't want them to be acting compositely. Wanted the in situ to be doing the work from a durability perspective. They quite like the idea of this extra layer of protection around the core. So that led to that being non-participating, and that's sort of when we moved to the next project, it was a case of, well, why have we got all these hooks sticking out of flat panels? It's only to hold them on and stop them falling off. So if we make it a box, they won't fall off. So that's part of the learning going through that process.
And actually, the shell itself, when you look at the concrete pressure, because that's again the case that we've had designed for, is a lovely little box element that that's why we don't need any 3 ties or that, because it's acting as a box effectively. You're putting stuff into hoop tension, so the reinforcement's right down small. So it's good from that perspective.
Okay, excellent. Thank you very much. Let's move to David and Ioannis. So Cod Little has a question. So I think this is relating to Nova East, I think. So when designing foundations so close to the Victoria line, is it necessary to agree a maintenance strategy in case of works on the tunnel, presumably at a later stage?
Usually that is included in the method statement of the contractor. And yes, in certain cases, if it is asked, we provide a maintenance scheme.
Yeah, I think the question is getting at, do you need to take into consideration, you're thinking about what future maintenance might be done on the tunnel? No,
that was not the requirement of not a requirement in our design. That is a part maybe for the permanent works designer.
Yeah. Okay. Thank you. And I like this one from Andy Truby. I'm reading it. Wow, that is really complex construction. What should the permanent works designer do to assist in the temporary works design?
I suppose it always varies project to project, but I think like the key thing is working collaboratively, because I think what you'd always find is the permanent works designer will design and detail a building up to the point it is almost ready for construction until the appointed whether it be a temporary works contractor sort of been, or demolition contractor sort of been appointed to it. So I think it's all about that real early engagement, because there'll be certain things that, whether it be a temporary work designer or a demolition contractor or even pilot contractor, they might have certain ideologies or methodologies that will change the different load paths acting on the structure. So I think it is key to get that early engagement, and always the best form of temporary works is no temporary works.
Yeah, that sounds good to me. Andy had a sort of follow-on question to that as well, which was, does the temporary case, including the tower crane for the core walls, generally add significant reinforcement to the core walls?
It depends largely on the geometry in plan and the regularity of the core. In that case, we had significant reinforcement, significant larger reinforcement requirements than the permanent case, and it depends also largely on the connection of the lobby slabs and how the core will advance ahead of the lobby slab, because if the lobby slabs are connected with a supposed pin connection, then the reaction of the core in different stages is totally different. So we had cases also that we had to add reinforcement like diagonal reinforcement, like we put in coupled beams in between walls for the temporary case. But yes, there is there might be cases that the additional reinforcement required might be significant. One case is also the top, the crown of the core, where if you put a tower crane on the top, you need significant reinforcement increase.
Okay, lovely. Thank you very much. The next one's back for John and Philip. So quite a long question here from Maria Kierzek. A question regarding bridge design toolkit. The issue of reducing building tolerances was mentioned. What was assumed for these semi-prefabricated bridges at midspan, considering the total amount of midspan displacements, which is the sum of effective settlements, deflections, and the mentioned tolerances, and what range of spans were analysed?
Okay, I'll take that one. In terms of the spans that have been analysed, we've gone down to, I think it was 15 metres and up to 35, although that has now been pushed a little bit further since recently. It's notable that some beam manufacturers are now doing 50-metre long W beams, which is quite something. In terms of the tolerances, as you sort of work your way up, one of the things that we've tried to do at an early stage is to fix the position of bars very closely. It's quite interesting because traditionally we specify bars at certain centres, and the steel fixers just go out and set off at 125 centres down a face. Here we actually need to position the bars much more closely, but by using the relevant jigs and that type of thing, we actually can get the bars much more. We have to position individual bars almost in place. We're then designing, where we need to, we put additional lap into the lap length into that position. So there's tolerance there. We're just thinking ahead what might not quite, where you might not get a perfect fit. What's interesting is as you come to the top of the columns, you've got these shells here, and then you come to do the diaphragm. And diaphragms, traditionally, you found, the contractor always complaining it's just taking longer than I thought it was going to. And then, next week's progress meeting, there's still fits in the reinforcement. What we found on these bridges here is that actually, because you've got that level of control coming out of the top of the shell, it's then easier to place the beams with the projecting strand out at the end and get them into the right place. And actually, I think it's almost, I think, Phil, you can correct me on this, but I think the contractor side has actually been quite surprised by how much quicker it's been, because everything that up to that point has come up under control. In terms of heading out to mid-span, we're into fairly conventional technology here with the precast beam bridges that have got tolerances set on them. They're obviously pre-tension beams, so in terms of lateral tolerance, it's fairly well fixed. Vertical tolerance can be a bit more unpredictable because it depends on the balance of the pre-stress and the creep, but that's fairly conventional. In the analysis that we're doing through the configuration tool, again, we're just looking at deflection doesn't tend to govern the design on these bridges, but again, we're looking at those various cases and making sure that comes through. I hope that covers the question there, but if not, come back to us.
Okay, thank you very much. Perhaps if I just stick with you, Jonathan, just one more quick one. I think you touched on this, I think, in your presentation, but your modular, the use of modular construction like that obviously very much drives the detailed design. So, does that use of modular construction mean that we need to start detailed design at a much earlier stage?
I think it's worth saying that it's thinking about detailed design as part of the development of the system, but thinking about it from my perspective, I think it's about thinking about the system as a whole that can be deployed to multiple projects. So in our normal workflow through a project, it's scheme design, and you're basically building up your detail as you go. I think the way that what we're finding at the moment is if we can develop a system, a kit of parts that you can deploy to multiple bridges and multiple projects, you have to think about that detail at the outset as part of that work. And I think there's an interesting sort of question about how you procure that. How do you actually go out to the market and say, we want you to go and design a system? And then what's the value of that system, and how does it get deployed across multiple projects? So it's a really interesting space at the moment in terms of that conversation. But you do have to think about reinforcement positions and having the modelling software to actually sit there and play in that sort of sandbox environment and play with those interfaces is really invaluable to that process.
Can I add a quick one to that? In that, very very early on, through the design of the HS2 bridges, it was clear that length of various laps would be a governing feature in the sizing of the components, for example. And so we did a lot of work very early on through there, and that's where the parametric model started to be developed to enable us to vary these things early and do that. But then what we've done through the Innovate UK project is to try and accommodate the experience from that and their experience of the work that we've done to this point, so that a designer coming in, where they can take the benefit of that and actually have the confidence that, yes, I should be able to get a lap length in there later, I should be able to do this, I should be able to do that. So that's captured through the design guide and through the output from the tool. So although detailed design sort of starts early, we've tried to jump a few of the hoops in there to not make it as big a jump in there, if that makes sense.
It does. Okay, thanks. Conscious of time, we do have 2 more questions, which for David and Ioannis. In fact, they're probably both for Ioannis, I think. So if you haven't typed in a question yet, we're not going to have time to deal with it probably. So we'll just take the 2 that I have. The first one is from Christy Milne, directed to you, Ioannis. It says, could you explain the precast detail interface with the wall and anchors for the tower crane a little more? How was this sequenced?
Okay, usually the cap of the course is a precast element. So the requirement from the contractor was the cap to be in place before the tower crane goes in, because there will be a handover, intermediate handover from the first contractor to the second one. So that inserted the problem, because the base of the tower crane will be higher by the thickness of the cap on the top. So the way to tackle this, and the way we did in this case, was to design the anchors that were going into the core and cast, of course, with the reinforcement of the core, and then pretension the stud below the steel grillage with the anchor. So we had some pretension in it, locking the anchor in the core. So therefore, we could minimize the effect of the standoff of the standoff distance of the anchor to the underside of the stud to the stud of the grillage. So actually, the problem is minimized down to a pull and push problem in a pre-stressed anchor.
Okay, thank you very much. And one last one. I think this is coming your way again, Ioannis. So, if you can be fairly brief, that would be good, because we're running out of time. So it's from Matthew Collins, and it's on the Belfast Bank building. How were the containers connected together, and what was the detail for connecting the facade to the containers?
So the containers themselves are designed according to some ISO standard in order to be able to be connected and locked together into the ship. So the ship also has a lateral movement. So this is already something that is already designed for us, and it was not far from the forces that we have. But for the containers with the additional backfill that we needed in order to accommodate the wind loads and the overturning, we added and we welded some additional bracing of the containers. We then designed a special connector that could be assembled with the lock nut of the container down to the foundation, and check the foundation for this. Because that had to be a much larger anchor, and check the foundation against punching shear and local moment stresses.
Brilliant, thank you very much. Very, very clear, very quick. Can I just sort of thank everybody, all our speakers again, both for your presentations and for your questions, and thank you also everybody for joining and making that a good interactive session, or at least as interactive as it can be on one of these. So just a couple of things just to close. Just to note that we are soon going to be launching our coolest concrete competition again. This is open basically for anybody in the first 10 years of their career as an engineer or as a postgraduate researcher. You need to submit a poster that just basically shows interesting use of concrete that you use to solve a design or construction problem, and there'll be a cash prize and I think a year's subscription as a young engineer to FIB, plus an opportunity to present your work at an FIB UK event if you wish to. You should all be sent a feedback survey shortly, so please do complete that if you can, because it really does help us to make our events as good as they can be. We can't actually share the slide decks themselves, but the on-demand version of the webinar is going to be available very shortly via the iStruct website. And if you've got any other questions, then please do contact the institution. So thanks everyone again. Have a great evening, and goodbye for now.